It is a great pleasure to announce the speaker of this special talk, Professor Gordon Slade from University of British Columbia. Professor Slade is a world-known researcher in mathematical physics and probability theory, whose profound work in the fields has shaped research over the last decades. And we are really fortunate that Professor Slade is the Clay Lecturer at the program Stochastic Systems for Anomalous Diffusion, which is taking place now in the Isaac Newton Institute for Mathematical Research. So Professor Slade has made important contributions in the study of critical phenomenon and phase transitions. In particular, I would like to mention his impactful work on the Lace expansion and on the renormalization group. The Lace expansion was introduced by David Bridges and Tom Spencer in 1985, and then it was greatly developed by Professor Slade. He has transformed the Lace expansion into a powerful, flexible technique for the study of high-dimensional critical phenomena, which appears in many mathematical models of interest in physics. Among examples, I would like to just mention models of percolation, random graphs, and the enumeration of self-avoiding random walks. More recently, but in an equally brilliant work, Professor Slade, together with his collaborators, have introduced a rigorous renormalization group method for the study of critical behavior in self-avoiding walks and spin systems. And we will hear more about this work in Professor Slade's.
Thank you very much. It's a pleasure to be here, and I'm also grateful to the Clay Math Institute and the Newton Institute for the opportunity to speak today. And yeah, I'm going to be talking about self-avoiding walks, spin systems, and renormalization. So let's just go straight to the self-avoiding walk. It's one of the simplest mathematical models that you can imagine to define. So maybe if you look at the picture here first, you see what it is. In the plane, I have a walk that takes nearest neighbor steps, either north, south, east, west, and it's not allowed to intersect itself. And we're looking at all of these non-intersecting paths. So that's Sn is the set of these non-intersecting paths. So omega is just a sequence in Zd. Zd are just the points in Euclidean space whose coordinates are all integers. And it takes nearest neighbor steps. So we'll usually start it at the origin. So omega of 0 is 0. That's the 0 in Zd. Takes nearest neighbor steps and no self-intersections. And we just let Cn be the cardinality of the set of all of those n-step self-avoiding walks. And to put some probability into it, we'll declare all the walks in Sn to be equally likely, which means that each walk has probability 1 over Cn to occur. Sometimes we're interested in focusing on where the walk ends, so Cn of x counts the number of n-step self-avoiding walks that start at 0 and end at x. And so here's a picture of a random 100-step self-avoiding walk, and here's a picture of a random 100 million step walk. So there are many reasons why you might be interested in this. If you're in enumerative combinatorics, then you might like to know, well, what is Cn? What can I say about Cn? If you're interested in computer science, you could ask, how can I develop an efficient algorithm in order to compute what Cn is? And also, how can I sample this space Sn when n is huge? So this space has got a size which is exponential in n. And so if n is 10 to the 8th, like it is in this picture, you have a sample space which has size, a base to 10 to the 8. It's a massive space, so how do you efficiently sample? If you're in probability theory, you could ask, this is an interesting looking curve, random curve here. What is the probability distribution of those curves? And one property that you see in the long curve that you don't see in the short one is that there's a scale invariance. There's a fractal-like quality to one of these long self-avoiding walks. And there's a scale invariance in the sense that if you look at a small piece of this walk, it looks the same basically as the large piece. And that goes on over all scales. And there's also a property of universality, which is that here I was working on the square lattice. If instead I had drawn self-avoiding walk on the triangular lattice or the hexagonal lattice or some other lattice, the small ones you would detect the lattice, like here you can see the square lattice in the walk, but here you don't, and you would see the same result for a long walk, no matter what lattice you picked. So that's the universality. If you're interested in polymers, then this is the standard model for, the standard baby model for polymer molecules. These are real two-dimensional polymers in the laboratory, and they look pretty similar to this. And in fact, the first serious scientific work on self-avoiding walk was done by Paul Flory, who's a Nobel laureate in chemistry, for his work on polymers. So there are many reasons to be interested in this. The fifth one, which I haven't mentioned yet, is the connection to critical phenomena in equilibrium statistical mechanics. And that's my own interest, and I'm going to focus on that aspect in this talk. Just to compare with what we're not talking about here, it's not simple random walk. So simple random walk is, you just start at the origin and choose a neighbor at random and step to it, and then choose a neighbor of your current location independently of what happened before and step to that new neighbor and continue like that. In particular, self-intersections are allowed, and in 2 dimensions, there's going to be a lot of them. So in 1,000 steps, you see something that looks like this, but after you take 100 million steps, then you don't see the lattice structure anymore. There's also this universality in scale invariance, which is a property of Brownian motion, which is what this limit is. And no matter what the dimension is, the root mean square displacement after n steps of this n-step simple random walk is square root of n. That's related to the fact that this is a 2-dimensional random fractal here. That the 2 dimensions is actually that same 2 there. And that property of being 2-dimensional will persist also in higher dimensions. So in 3 dimensions or 4 dimensions, 5 dimensions, whatever you like, the Brownian path will almost surely have dimension 2. That's going to be relevant for things I'll be saying later. So I mentioned enumeration. What can you say about Cn? How far can you go? How many n's can you handle? And this is it for d equals 3. People have been working on trying to count these things for at least 60 years. And for d equals 3, the highest number is 36, where, just to save you counting, that's about 3 times 10 to the 24, 36-step walks. We don't know how many 37-step walks there are. The number of digits here is growing linearly, so that's exponential growth. And indeed, it's an easy consequence of this inequality, so that you do have exponential growth. So this inequality says, the way to understand that is that Cn times Cm is the number of ways that you can take an n-step walk, self-avoiding walk, and join on to the end of it an m-step self-avoiding walk. When you do that, you'll get all the n plus m step self-avoiding walks, but you'll also get more. So you get that inequality. And if you take the log of Cn, it will therefore form a subadditive sequence, and then you can appeal to a lemma about subadditive sequences called Feketa's lemma to tell you that Cn to the 1 over n has to converge to some limit mu. That's just a simple consequence of this. It's a basic fact from analysis. Cn to the 1 over n converges to a limit mu, which is called the connective constant. It depends on the dimension. It also depends on which kind of lattice you used in order to model your self-avoiding walks. And you get for free a lower bound on Cn by mu to the n. That holds for every n. Now you could ask about upper bounds. So in 1962, Hammersley and Welsh proved this upper bound. Cn is bounded above by mu to the n e to a constant times root n. And they'll tell you something about the constant as well. Well, for low dimensions, 2 and 3 and 4, this has barely been improved since 1962. Harry Keston made a small improvement to this square root of n in dimensions 3 and 4. More recently, there have been other, let me say, modest improvements to this upper bound, but still very far from what we think is the truth, which I'll tell you in a moment. So the truth involves critical exponents. And to define those, I want to introduce the susceptibility and the mean square displacement. So the susceptibility is just the generating function for the sequence Cn. You know, if you're interested in the asymptotics of a sequence, it's often a good idea to form the generating function for that sequence and look at how that generating function diverges at the closest singularity to the origin. That will tell you something about how your sequence is behaving for large n. So let's do that. It's called chi. And the mean square displacement is just the average distance squared for an n-step self-avoiding walk. And because Cn is growing like mu to the n, the radius of convergence is 1 over mu. So there's a huge body of evidence, although not so much in the way of theorems, that tells us that there are universal critical exponents, gamma and nu, and that's part of a family of critical exponents that are interesting, that describe the asymptotic behavior of Cn, chi, and Rn. So Cn grows like a multiple of mu to the n to the gamma minus 1. That corresponds via that correspondence I was mentioning before to the behavior of the generating function as being blowing up like this. The same exponent, these gammas are the same. And the mean square displacement should grow like a power. And there are very precise predictions for what these powers should be. So in 2 dimensions, gamma is exactly equal to 43 over 32. It's not proven, but it's a huge body of evidence for that. Nu 3/4. So these rational values are typical of what you see in models of critical phenomena in 2 dimensions. In 3 dimensions, these are from numerics by Nathan Clisby, who's the person who did the simulations behind the pictures I showed you earlier, who has computed gamma and nu using Monte Carlo to high accuracy, where these numbers are his estimate for the uncertainty in the last 2 digits. So the parentheses indicate the uncertainty in the last 2 digits. Whereas for d greater than or equal to 4, you get gamma equals 1 and nu equals 1/2, which are the same exponents as you would see for simple random walk. So for simple random walk, the number of simple random walks of length n is just 2d to the n. There's no polynomial approximation, so gamma is equal to 1. And the mean square displacement, the root mean square displacement grows like a square root, so nu is 1/2. And in 4 dimensions, there are logarithms predicted. So you might wonder, what's the big deal about these exponents like n to the 3/4 versus n to the 1/2? Does it really make a big difference? Well, here's a 2-dimensional 100 million step self-avoiding walk and 100 million step simple random walk to scale. That's the simple random walk there. That's not a fly on the screen. So I'm basically telling you that the 4th root of 10 to the 8th is 100. But what you see is that this red walk is 100 times 100 times bigger than the blue one. So these exponents actually matter. Now, what can you prove? So here's a theorem that Takashi Hara and I proved long ago, that for d greater than or equal to 5, the scaling limit of self-avoiding walk is Brownian motion. And Cn grows purely exponentially, so there's no n to the gamma minus 1, or gamma is equal to 1 if you like, and the root mean square displacement is growing like the square root, just like simple random walk does. And the method of proof is the Lace expansion that was introduced by Bridges and Spencer. Yes?
Mu is non-universal.
Mu is not universal, that's right. So the upper critical dimension is 4. That's connected with the fact that we see these simple random walk exponents appearing above 4 dimensions. That's what we mean by that. And you can kind of guess this by saying, well, Brownian motion paths are 2-dimensional. And so if I take a Brownian motion path and try to concatenate onto the end of it another Brownian motion path in dimensions bigger than 4, they generically won't intersect anyway. And so if you tell a self-avoiding walk that it shouldn't intersect, or tell a simple random walk that it shouldn't intersect itself, it'll say, well, thanks for the advice, but I wasn't planning on intersecting myself very much anyway. And so they end up having the same behavior. Now, in lower dimensions, this will not be the case, but the theorems are really very, very poor as far as comparison with what the predictions are. So the best upper bound in dimensions 2, 3, and 4 are that Rn is not n. So self-avoiding walks are not straight lines. No control over the error here. So in particular, it's not proof that Rn is less than n to the 0.9999, and you can add as many nines as you want there. It's still not proved. And for the lower bound, something very obvious has not been proved, which is that because a self-avoiding walk can't intersect itself, it must be exploring new territory, so on average it should go away at least as far as a simple random walk. But that hasn't been proved either. So given this state of affairs, it's maybe a good idea to look for another model that's more tractable, but which lies in the same universality class as the self-avoiding walk. So let me talk about that next.
So, sorry, Gordon, just
Yeah.
comment on the question. So you showed this strict self-avoiding walks, and there's the Brownian motion, but you can have things in between, right? You can have like a less strict self-avoiding walk.
Yeah, so let's talk about that now. That's the weakly self-avoiding walk. Thank you. So there's more than one version of the weakly self-avoiding walk. I want to talk about the continuous time version. So this adds an extra level of randomness to the underlying random walk. So it's not just random in terms of where the next step goes, but it's random in terms of what time the step takes place. So what we do is we associate a Poisson process to each point. You can just think that at each point in ZD, there's an alarm clock that goes off at a random time. It's actually a very poor quality for an alarm clock, but it goes off at a random time, and when that alarm clock rings, then a step is taken to a randomly chosen nearest neighbor. So it's a rather small modification, but it's useful to have that extra level of randomness. So x of t denotes the position of this continuous time simple random walk at time t. Starts at the origin. And then we'll define a random variable, I of t, which is called the self-intersection local time. It's the double integral over s and t of counting 1 here. This will be equal to 1 when the walk is at the same location at time s and t. So this is kind of accumulating double points, so to speak. And it's a measure of how much the walk intersects itself. The more it intersects itself, the bigger this I is going to be. So this is a random variable. And then we introduce a parameter g, which is the strength of the interaction, and define the ct, which depends on g, to be the average. So this e is averaging over all the simple random walks. And we weight the walk according to the self-intersection local time in the exponent here. So walks with big self-intersection local time will count less compared to walks with smaller self-intersection local time. And this is an analog of Cn that we had before. And then the generating function now, because n has been replaced by t, which is a continuous variable, becomes a Laplace transform. So we define the generating function, or the Laplace transform of this function Ctg in this way. And again, there's a subadditivity argument that tells you that there's a critical value of nu, which is negative, in fact, such that this Ct to the 1 over t converges to e to the nu, and the susceptibility, which is what we'll call chi, is finite if and only if nu is bigger than nu c. So the weakly self-avoiding walk is predicted to be in the same universality class as self-avoiding walk, no matter what g is. So even if g is very small, this should behave like the strictly self-avoiding walk, not like simple random walk, in terms of all the exponents and scaling limits being exactly the same thing. So here's a theorem that goes in that direction. We proved with Bauer-Schmidt and Bridges that for d equals 4, so d greater than or equal to 5, we already understood for the strictly self-avoiding walk, so I'm trying to move downwards now. For d equals 4, and we have to take small g, because there's a kind of a perturbative approach to the problem, that as nu approaches nu c, so I'm letting t be the deviation of nu from the critical value, the susceptibility blows up linearly, but there's a logarithmic correction with a power 1/4. And so the proof is based on a rigorous renormalization group method. So Ken Wilson got the Nobel Prize in 1982 for his work on renormalization group, which he developed in the early 70s. Suppose you wanted to go below 4 dimensions. Well, there's this wonderful idea from physics, which is that what you should do is think about the dimension as being a continuous variable. So, and look at d, which is close to 4. And well, I love the title of this paper, Critical Exponents in 3.99 Dimensions by Wilson and Fisher, where they say critical exponents are calculated for dimension d equals 4 minus epsilon with epsilon small using renormalization group techniques. And the exponent gamma is calculated to order epsilon for some spin models of the type that we'll introduce shortly. And nowadays, this so-called epsilon expansion for the exponent is known at least up to order epsilon to the 6th. But mathematically, some questions arise. Like, what are we really talking about here? What happens is that the exponents get written in such a way that d makes sense as a continuous variable, and so you can make some sense out of it in that way. But if you really want to study self-avoiding walk in 3 dimensions using this from a mathematical point of view, it seems very hopeless. Like, for one thing, this expansion cannot converge. It's certainly divergent because gamma is constant for d greater than 4. And so it's not an analytic function at d equals 4. At d equals 4. So this is asymptotic only, etc. So this is intriguing, but from the mathematical point of view, it's pretty puzzling. Here's another idea which is related, which goes back to the same era. So Fisher, Ma, and Nickel in the US, and at the same time Suzuki and his colleagues in Japan in 1972 did something similar, but it's going to be easier to make sense of it mathematically. So what they did was they said, let's look at long-range models. So let me first of all define what we mean by a long-range simple random walk, and then we'll talk about the self-avoiding version of it after. What is a long-range simple random walk? Well, it's just a random walk which is allowed to step not just to the neighbors of its current position, but it can step anywhere in all of ZD. But the probability that it makes a very long step is going to decay, like if the length of the step is r, like r to the minus d plus alpha, where alpha is between 0 and 2. And in particular, that step distribution does not have a second moment. So the variance is infinite. And so you're going to see some very long steps. One way to implement this kernel here is to look at a fractional power of the Laplacian. So that's the way I like to think about it. So the probability that your next step is to y, given that you're now at x, is given by the kernel of this alpha over 2 power of minus the Laplacian, which has exactly this decay that we were trying to capture here. So that's kind of a concrete realization of the step distribution. And if you look at what the walks look like in 2 dimensions here with alpha equals 1.1 and 10 to the 5th steps, you see these huge jumps that are taking place because of the fat tail of the step distribution. Okay? The fact that the variance is infinite means that every once in a while you're going to take a huge step. And then you'll explore where you are for a little while, and then you'll take a huge step and find some new territory and so on. And you can ask about what's the scaling limit of this long-range simple random walk. For nearest neighbor case, it was Brownian motion. Here, it's a class of processes, stochastic processes that are very well studied, called alpha stable processes. And if you look at the path more precisely, if you look at the set of points, so the edges, the steps are drawn here just to show what's happening. But really, I'm just talking about the vertices. The vertices form a set of dimension alpha. So it's a fractal set, alpha's between 0 and 2 strictly. But generically, two of these things are not going to intersect each other in dimensions bigger than 2 alpha. Okay, because same argument as before for d equals 4 being the upper critical dimension. So you can now define self-avoiding walk or weakly self-avoiding walk based on this long-range random walk. And Marcus Heidenreich in 2011 proved a theorem that says that in any dimension greater than or equal to 1, if you choose alpha less than d over 2, so actually let's think about dimensions 1, 2, and 3 because this should otherwise be a d over 2 min 2. In other words, if you're above the upper critical dimension, the long-range self-avoiding walk indeed converges to an alpha-stable process. But now we can use that idea of Fisher, Ma, and Nickel and Suzuki to try to go slightly below DC in the following way. So for d equals 1 or 2 or 3, make this strategic choice of alpha here, 1/2 d plus epsilon, so that if you solve this equation for d, you find that d is 2 alpha minus epsilon, which is dc minus epsilon. So you're a little bit below the upper critical dimension, and yet you can still work in an integer dimension where you know how to define things. So instead of working in 3.99 dimensions when the upper critical dimension is 4, you work in 3 dimensions where the upper critical dimension is 3.01. But you don't have to actually look at 3.01. You don't have to define a model there. So in that case, I proved this theorem that the susceptibility for the long-range weakly self-avoiding walk, so where x of t now takes these long-range steps, is bounded above and below by inverse powers of t, where the powers are given in an expansion in small epsilon. So epsilon is small here, and g, which is the strength of the interaction, is also small. T is how close you are to the critical point, and the susceptibility is blowing up as t goes to 0. And the short version of this is that we're calculating the exponent gamma to order epsilon. Okay, so I hope to have time to say something about the method of proof there. But in order to do that, I have to talk about spin systems first, because as it turns out, there's not just a kind of a qualitative connection between the self-avoiding walk and the spin systems, but it's actually quantitative. And this has been understood in physics for a very long time, but let me try to explain some of that slowly. So first I want to define the Ising model. Just for reference, we won't be talking about the Ising model very much later. It's more a kind of a variant of it, the phi to the 4th model, that's going to be important for me. But it's easier to draw pictures for the Ising model. And this is one of the most fundamental models in equilibrium statistical mechanics. I don't know how many papers have been written on it over the last 100 years, but it's a mind-boggling literature in its size. You need to define it first in a finite volume. So take a finite box, lambda, and then you assign spins which are either plus or minus 1. So at point x, you have a sigma x, which is plus or minus 1. You assign spins to the vertices. And define the discrete Laplacian to be this. And then the energy of the entire configuration sigma is given by this quadratic form, which you can rewrite in terms of a constant, which doesn't matter, as minus the sum over neighboring pairs of sites, x and y, so x and y, which are neighbors like that, sigma x, sigma y. And at temperature T, the probability of this distribution, of a particular configuration sigma is given by the Boltzmann weight, which is proportional to e to the 1 over t times minus the energy. So the constant cancels out top and bottom. So configuration sigma are more likely when sigma x, sigma y is plus 1 rather than minus 1. So neighboring spins like to be aligned in order to minimize the energy here. And that leads to a picture like this, which many of you will have seen before, I expect, where here the spins, instead of being plus or minus 1, are white or blue. And I've drawn in a rectangle here boundary conditions that fix the spins on the top half of the boundary to be white and on the bottom half to be blue. And if you vary the temperature, you see different phenomena. So if the temperature is low, then the effect of the boundary penetrates deep into the bulk and there's a phase separation so that the top is basically all white and the bottom is all blue. There are little dots of blue there which will have inside them little dots of white and so on. But the predominant effect is that you have a white phase and a blue phase. Whereas if the temperature is high, then the boundary condition does not penetrate into the bulk at all and you just see random blue and white. It's just noise. And the transition between this kind of behavior of phase separation and this randomness is taking place at a specific definite temperature Tc, the critical temperature called the Curie point, where you see this very interesting fractal behavior. So this is the phase transition which is taking place at this temperature. And here you see structure on all length scales. Okay? And there's this self-similarity and also the universality that we were talking about earlier for the self-avoiding walk. So as I say, I'm not really going to talk about the Ising model specifically, but rather this relative of it, which is really a close relative, but it's also a generalization, where we replace the Ising spin, sigma x plus or minus 1 at each vertex, by a vector. You can think about n equals 1, but I really do want to consider to be this variable n, which is the dimension of the spin, to be a parameter. So there's a vector phi x in Rn at every point in the lattice or in the finite volume, and then we have to take a thermodynamic limit, whose probability distribution initially is given in terms of this double well potential. So G is positive and nu is negative. And so the exponent up here is the red one, and its exponential is the blue one. And so if you think about the case of n equals 1, you have these peaks here, which are telling you that the phi x, if n equals 1 is just a real number, likes to be either here or here, rather than in other places. It has the preference to be underneath those peaks. And so it's kind of like plus or minus 1 that we had before. But we're generalizing it to an unbounded continuous spin, which might also be a vector. And then we have this formula here, which is maybe the most complicated formula that I'm going to be writing down today. So we define a probability measure on all of the spin configurations. So a spin configuration is Rn to the lambda. At each point in lambda, you're going to put a spin. The single spin distribution is given by what we were just talking about. It's that bimodal distribution for n equals 1. And then there's this interaction, which is like the Ising interaction here. And maybe the good way to think about this is to put the product up into the exponent as a sum and then do summation by parts. Then the exponent will become it'll become e to the minus gradient phi squared. So spin configurations where there's big gradient in phi will be diminished relative to ones that have a small gradient. And so spins like to align, in other words. And there's again a phase transition, which is associated to a critical value of this nu, which will be negative. So now we want to be driving nu negative until we see the phase transition. And for nu below that critical point, I mean, this is not a simulation. This is just a hand-drawn image that the spins are basically aligned, whereas if nu is bigger than nu c, they're not aligned. So we can define the susceptibility. It's the infinite volume limit of the sum over all x of the correlation between the spin at 0 and the spin at x. So the idea is that as your nu is approaching the critical value, the correlations between the spins is going to be getting higher and higher. And at some point, this sum will therefore diverge. And that will happen at the critical point, in fact. The 1 over n here is just a convention, which is convenient. And the predicted behavior is that as the nu gets close to nu c, so t is the difference, the susceptibility will again blow up like 1 over t to the gamma, where gamma can depend on the dimension, and it can also depend on n. And there's a universality conjecture, which is that the critical behavior, like for example this gamma, will be, first of all, independent of g. And if n equals 1, it'll be the same as for the Ising model. If n equals 2, it'll be the same as for the xy model, which is the model where this single spin distribution, instead of having this phi to the fourth distribution, is just uniformly distributed on a circle or on a sphere, the Heisenberg model, and so on. And it's also independent of the lattice and other fine details. So it's a big problem to prove this. And here's one thing that we proved in dimension 4, that for small g and for any n, the susceptibility blows up, again, linearly. So that's like gamma equals 1, but there's this log correction, and now the nature of that correction depends on the number of spin components n. So the log has a power n plus 2 over n plus 8. And, well, these log corrections were predicted long ago, and there are some early results from the 1980s for the case n equals 1. We can do the same thing with long-range models. Try to go below the upper critical dimension. So 4 is the upper critical dimension for the phi to the fourth model or the Ising model. Suppose you want to go a little bit below. We can use long-range models to try to do that. And so there we take this quadratic form in the Hamiltonian and replace the Laplacian by a fractional power of the Laplacian here. So alpha between 0 and 2. This changes the upper critical dimension to 2 alpha. And so we can try to study, again, d equals dc minus epsilon for small epsilon by just choosing alpha appropriately as a function of the dimension. And prove this theorem that the susceptibility for the phi to the fourth model with n-component fields blows up like an inverse power of t, where that power depends on epsilon and alpha and n I mean, the short version again is here, that gamma up to order epsilon squared is given by 1 plus n plus 2 over n plus 8 times epsilon over alpha. And there are many, many other people who have worked on this kind of problem. Okay, so how do you bring these two things together? I've been talking about self-avoiding walk, and then I was talking about spin systems. We had some theorems that looked kind of similar, but the models initially look rather different. So what is the connection? Well, Pierre-Gilles de Gennes, who was a physicist, got the Nobel Prize in Physics in 1991 for his work on polymers, wrote a short paper in 1972 where he said the self-avoiding walk model is the n equals 0 version of the n-component spin model. Why is that? Why did he say that? Here's a kind of a, cartoon of the reason that you can take the susceptibility of an n-component spin model and write it as a kind of, in a sort of random walk representation where there's one random walk, which is a self-avoiding walk, which is joining 2 points, and you're summing over one of the points. Well, the other one is the origin. And then there's like a gas of loops. And those loops carry a factor n. Each loop has a factor n in it. So if you just put n equals 0, then the loops will disappear, and you just have self-avoiding walk. So that basically solved the self-avoiding walk problem from the point of view of physics if you've already solved the spin system, because all you need to do is take every formula that you know for the spin system, put n equals 0, and then you have a conclusion for self-avoiding walk. For example, if you look at what we saw in a previous slide for the susceptibility exponent for the n-component spins, there was this n plus 2 over n plus 8, and if you just put n equals 0, you get 1/4, which was the answer that we had for the self-avoiding walk theorem that matched that, the long-range theorem. But, mathematically, what is a zero-component spin? How would you take a limit as n goes to 0 if n is 1, 2, 3, 4, 5? So, there are issues if you want to prove theorems. But there's another idea, and another Nobel laureate, actually, who's behind it, Parisi and Surlith in 1980, and simultaneously and independently McKean, said one way to get n equals 0 is to, let n approach 0 from above, but another way is to add n and minus n. And what they noticed is that if you take an n-component boson field, which is just the usual field phi that I was talking about before, that's a bosonic field, it contributes a factor n for every loop. That's what de Gennes said. But if you use a fermion field, which is a field which is given in terms of an anti-commuting Grassmann variable, then it contributes minus n for every loop. And so if you combine them, if you have both, then the loops all cancel each other out and you just end up with self-avoiding walk. And David Bridges and his student Ismael Munoz-Maya in 1991 proved a rigorous version of this statement that says that the weakly self-avoiding walk in continuous time, which is what I defined before, and actually this is the reason that we're using the continuous time version, is so that we can appeal to this equivalence here. The weakly self-avoiding walk is given by a supersymmetric version of the phi to the fourth model with 2 bosons and 2 fermions, so n equals plus or minus 2. And let me show you just the formula. So I won't be proving anything here, but just to show you a formula that kind of might make some connection. So look at a d-dimensional torus, discrete, and assign to every point in this discrete torus a complex field now. So at point x, there's a phi x, which is a complex number. So now the spin is a 2-component thing, but I'm treating it as a complex number. And associated to that field, define a 1 form d phi x. And then define differential forms, tau x, which is phi bar, bar being the conjugate, plus 1 over 2 pi I, which is just a bookkeeping thing, d phi x wedge d phi y phi x bar. So basically, many people would do this using Grassmann variables, which are anti-commuting. This is a way of making those Grassmann variables very concrete, just in terms of differential forms. So these are taking the role of the Grassmann variables, if you're familiar with that kind of thing. So that's tau x. It's this differential form, and tau delta has got a minus delta sandwiched in between each factor, each term. And if you want the long-range model, then you replace this minus Laplacian by minus Laplacian to a fractional power. And then there's this wonderful identity that the infinite volume susceptibility is given by, well, this infinite volume limit. We're going to take the torus and let its size go to infinity. Sum over all of the points in the torus. There's a phi bar 0 phi x. And then there's an integral over c to the lambda, so that means the number of terms in lambda, number of sites in lambda, e to the minus this sum, like that. So a couple of things about this formula. First of all, if you plug in the tau squared, you're going to get a phi to the fourth term from here. In the tau, you'll have this term here, which is like what we had in the phi to the fourth model. There's also like a phi squared term, which is coming from the new tau here from this part. But there's also all of these fermions, I'll call them, the one forms. And you'll notice that there's actually no measure here in this integral. So you have to construct the measure in the following way from this formula. What you do is you think of this for fixed phi as a function of the d phis and d phi bars, and just expand that out in a formal Taylor series, which will truncate because this product is anti-commuting, and so you can't have any repetition in the product. So it'll just be a polynomial in d phi and d phi bar. And out of that big polynomial that you get when you do the expansion, just keep the terms that have 1 d phi and 1 d phi bar for every single x in lambda. Just throw away the rest. That constructs a volume form, and then do a Riemann integral. So this is well defined in that way. going through it a little bit quickly here, but it is well defined. It's not the way you want to work with this. It's nice to know that it's well defined, of course, in order to have some mathematical object that you can do things with. But we can manipulate this very much like the phi to the fourth measure and treat the case where the fermions are present alongside the ones where they're not. And then the n's that come into the calculation when you do that, when the fermions are there, come in with minus n's also, and they cancel, and it's like n equals 0. Okay, so I have time left to talk a little bit about how these theorems are proved. I'm going to be rather schematic about this because it's kind of a long story, but just to mention some key words. So basically, we've got a problem of Gaussian integration here. So let's think about the case n equals 1. So we've just got a single component phi to the fourth model that I'm talking about. Let's look at the long-range model and work on a discrete torus whose side length is L to the n, fix some L bigger than 1, and we're eventually want to let n go to infinity, okay, to get the infinite volume limit and compute the susceptibility. So I introduced some notation here. Z naught is e to the minus v naught, where v naught is given by the sum over x of this single spin potential. So you should think of nu naught as being negative. And then the real problem that we have to solve here is how do you evaluate a certain Gaussian integral, which is Zn of phi, is this Gaussian integral of Z0 of phi plus zeta. So the phi is treated as a constant field here, and this Gaussian integration is integrating out the zeta. The C, which is the covariance of the Gaussian measure, is the resolvent of the inverse, it's of the fractional Laplacian together with some mass term to make it invertible. It's a bit of a detail that there needs to be an m squared there that gets disappeared later on. And what this Gaussian expectation represents is this kind of an integral here. So if f is a function on r lambda, so zeta is like a field on lambda, then it's just doing this, C inverse is just this minus Laplacian and plus m squared. So it's recreating what we had in the phi to the fourth measure earlier. So I'm saying that if you can figure out how to do an integral like this, you're going to be in business for calculating the susceptibility. Now, I've used this term universality and scale invariance, and that comes into the way that we think about how to do this integral, which is to make a good choice of the covariance decomposition, which is going to somehow capture the notion of the self-similarity. So this C, we decompose as a sum. N, remember, the scale of the torus was L to the n, so n is going to infinity eventually. We decompose it as a sum of covariances Cj. And before I talk about the properties of those covariances, it's just a fact about Gaussian integration that when you have a covariance C, which is a sum of covariances like this, then the field which you're integrating, which is the zeta, decomposes into a sum of independent Gaussian fields where zeta j has covariance Cj. And so you can then do the integration in a progressive way or in an integrated way where you write the zeta as a sum of zeta 1 through zeta n, and you first integrate out with the Gaussian integral with covariance C1, you integrate out the zeta 1, leaving the others fixed. Then you integrate out the zeta 2, and so on until you've done them all. And now about the properties of this covariance decomposition, we want the Cj's to basically, it's not literally true, but basically they're just rescaled versions of some particular covariance. And they're rescaled in such a way that C1 is capturing, this zeta 1 is going to be fluctuating on the scale of individual points, or zero blocks as I'm calling them here. Whereas zeta 2 will be relatively constant on 1 blocks, so blocks of this size, but fluctuating on a larger scale. Zeta 2 will be relatively constant on blocks of this size, zeta, and so on. And so as you do this huge multiple integral, what you need to understand is how you do a typical one in the middle. And so the integration of a single scale is via this mapping that takes zj to zj plus 1, where zj plus 1 is just the integral of zj with respect to this Gaussian measure with covariance cj plus 1. And we start with e to the minus v0. So Wilson's idea was that at the critical point, you have scale invariance, and that corresponds to a fixed point of this mapping. So if you have scale invariance, when you integrate out a scale and then do the next one, it's the same problem that you're solving the second time. So you have a fixed point of this mapping from zj to zj plus 1. And if it's a stable fixed point, which has some domain of attraction, that corresponds to a universality class, that all of the sort of interactions which are in that domain of attraction are going to be drawn to the fixed point and have the behavior which is associated to that fixed point, which includes critical exponents which can be computed from this mapping at the fixed point. Now, this becomes a dynamical system in infinite dimensions, and you need some reasonable coordinates in order to focus on the important part of the dynamical system and have some leftover part that you can ignore. Well, you won't be able to ignore it, but you have to work hard to prove that you can ignore it. So there's some good coordinates, which is that the leading behavior of Zj is just e to the minus Vj, where Vj has what are called renormalized coupling constants. So we started with G0 and nu 0, and now we have Gj and nu j. And the idea is that if you make this approximation and you do the integral of e to the minus Vj, you'll get e to the minus Vj plus 1. Now, there's an infinite dimensional coordinate that we call kj that controls all of the errors. And you know, that's in red to denote danger there, that there's a lot of work that needs to be done in order to control that, which I'm not going to be talking about. And the good variables for Vj are rescaled. So here I'm talking about the long-range model, where we have this epsilon, so we're below the upper critical dimension 2 alpha by amount epsilon when we're in our fixed dimension d equals 1, 2, or 3. And we should rescale the g and the nu according to these L to the epsilon j or L to the alpha j. And then when you do this computation about how Vj plus 1 is determined by Vj, you find that in particular Sj plus 1 is given in terms of Sj in this way to quadratic order. And this equation has two fixed points. There's a Gaussian one, which is S bar equals 0, which turns out to be unstable. And there's this non-Gaussian one, which is the other solution to this equation, which is this positive value. And that one turns out to be stable. And so we study this dynamical system of how these coordinates S and mu, which are describing those renormalized coupling constants in the potential, evolve together with the evolution of this infinite dimensional coordinate k. So the stable fixed point is what's called the Wilson-Fisher fixed point, and this RG map, renormalization group map, has that point as a fixed point. And so we're in kind of a dynamical system. It's hyperbolic for epsilon positive. It looks like this. There's a stable manifold that flows to the fixed point, and the critical point corresponds to the stable manifold. So in a way, you have to compute the stable manifold to know what is the critical point. You know, if you're doing percolation, for example, then you have this sort of extrinsic definition of what the critical point is. It's the point where you have the onset of infinite clusters. Here, we don't have anything like that. You have to find the critical point as part of the problem, and it's a point that lies on this stable manifold, so that when you follow the flow of the dynamical system under the renormalization group map, you will flow to the fixed point and not get outside the domain of the renormalization group map.
And this picture is an infinite dimension.
It is. Yeah. So the blue manifold is infinite dimensions, and the unstable manifold has dimension 1. Okay, so there's a whole story there, but I want to leave a few minutes for questions, so I'm going to stop at this point and just thank you and mention a couple of references. So in particular, this talk is more or less based on this paper here, which I draw to your attention. So thank you very much.
Questions?
Can you go back to slide number 7?
Yes?
The question on some constants A. So I wanted to know if it's possible to compute this A constant.
Yes, so A in dimension 5 is between 1 and 1.493.
But you don't have an explicit formula or series of...
We have a formula for it, but you can't really compute that formula. In terms of series, I've always had an interest in 1 over d expansions. So this is maybe it's an unnatural interest, but you can try to compute mu as a function of the dimension for large dimensions. So for simple random walk, mu is just 2d. For self-avoiding walk in high dimensions, the main effect is to rule out immediate reversal, so it's going to be 2d minus 1, but then you have to rule out squares, and so there's another term. And so there's an expansion in powers of 1 over d that you can write down that will presumably be a divergent asymptotic expansion. So there is an asymptotic expansion for A and for mu in powers of 1 over 2d to all orders with integer coefficients. And the coefficients are known for A, I think, for 13 terms. And they get very big. Yes.
Speaking about the easing point,
Yeah.
I've always wondered how people can able to calculate what happens at the critical point without knowing the value of the critical point.
Well, so we write down in our work, and I think other people who do renormalization group would also do the same, a formula for the critical point, but it's an infinite series. And in fact, it's given by in terms of a fixed, in this particular problem that I was just talking about, it's given in terms of the fixed point of a mapping in a Banach space. It's one coordinate of that. So it's not very explicit, but you just need to know it exists. You don't need to know what it is. Yeah. In fact,
but do you need to know how it is defined?
Well, it's once you prove that the susceptibility blows up at that point, then that point is the critical point, right? The susceptibility will be finite above the critical point, and so by definition, it's the point where the susceptibility blows up, where your correlations become bigger and bigger until it actually diverges. Yeah, it's like in this theorem at the top, we don't know exactly the value of mu, but you could still calculate gamma. There's an implicit equation which is obeyed by mu. That's how that expansion that I was mentioned was derived. I should say that I haven't really focused on what the value of mu is. So mu in dimensions up to, I don't know, 10 or 12 or something like that is known within a couple of percentage points, okay, rigorous upper and lower bounds. And it's certainly an interesting mathematical problem to think about the value of mu, even though it's not universal. Several people have worked on that, including one person in the room here, Jeffrey Grimmett, has been interested in that question, as have I.
There's a simple physics question. So the long random walk case,
Yeah.
so we make large jumps. I guess it's not a sort of equilibrium model, right? I mean, is there detailed balance in that model?
Yeah.
Yeah, it's detailed balance.
Yeah, it's a perfectly good random walk model.
So I guess in some fields of non-equilibrium physics, where you don't have detailed balance.
Mhm.
I don't know. Yeah, can you explore around and what sort of moves are doing a balance? And can you say interesting things mathematically about those?
Personally, I can't.
Or not the field?
Yeah, I'm not really familiar with that body of work, if there is one.
Yeah, so you started with this self-avoiding walk, and then you went to weekly self-avoiding walk.
Right.
This is not as tractable.
Mhm.
So, I mean, can you say what are the challenges, to go from one to the other?
Well, if you look at the theorem that I mentioned, there's that small g. Right? So in a way, the fact that you're seeing self-avoiding walk behavior for small g, it should be almost more difficult than for large g, because for large g, that means you have a stronger repulsion. You should be more like the strictly self-avoiding walk. Here you're as far away as possible from the strictly self-avoiding walk, but you're still seeing the self-avoiding walk behavior. But the small g allows you to do things perturbatively. So if you wanted to take the limit as g goes to infinity, you would not be able to use any of the methods that we're talking about. The one exception is this theorem with Hera, where there's no small parameter, but that's because you can't see the small parameter. It's sort of hidden. In that this theorem should be true for d greater than 4. Meaning if you could make sense of 4.1 dimensions, then the theorem should also be true there. But our method would never prove that. We're just kind of lucky, not very lucky, because the proof was computer assisted and quite long in order to do very concrete calculations of simple random walk quantities that were needed as part of the proof. But we needed something to be small in order for this proof to work, and it turns out that in 5 dimensions, that thing was just small enough to make it work. Yes?
Maybe slightly silly question, but so like these renormalization group methods for 5-4, for example, why did it only happen so late, the progress? For example, understanding these log corrections for D54.
Well, so if you ask a physicist, they would say, well, it was actually understood in 1972. So, but from a mathematical point of view, well, if you look at the proofs, you might get some idea about it. It's heavy. It's heavy stuff. So it's a lot of calculations, and it's very difficult. I don't know why somebody else didn't do it, but that could be related. There was a lot of work in the 80s, Gabetsky, Kupianin, Hara, and Tasaki, for example. There was a group in Paris at the École Polytechnique, Emmanuel Seigneur, Rivasso, Feldman, my colleague at the University of British Columbia. So there was a kind of a flurry of work in the 1980s. But then I think a lot of the other work that's been done on renormalization group has focused on two-dimensional models, dimer systems, easing models that are not nearest neighbor. So Giuliani, Mastro Pietro, for example, Toninelli. So there has been work in the renormalization group going in that direction more recently.
And like follow-up question, all this 80s constructive field theory work, how is it in any way different to this approach to RG, or is it?
Which one?
Some of this 80s constructive field theory.
From the 80s. Yeah, no, this is very much in that tradition. Flim and Jaffe, yeah, it's very much in that tradition. David Bridges comes out of that, and he's been doing this kind of thing since 1990. So I was happy to join him, something like 15 years later.
Any further questions? If not, let's thank Professor Slade again for a wonderful presentation.